Great. Okay, so thanks, Natalie. Thank you for the invitation to be here, and apologies as a Brit for bringing the rain with me, but we've really had enough of it back home, so an opportunity to ship it out somewhere else is welcome. So my name's Phil. I work on Swift, or the Neil Gerald Swift Observatory, as it's now called, in reflection of the fact that it's a lot more general purpose now than it was originally. This is Neil Gerald. I like this picture, partly because it's got Neil in it, and partly it just gives you an idea of scale quite nicely. This is Neil in the clean room standing in front of Swift itself. So what happens if I press that button? It goes forward. Good. I hope this slide is kind of meaningless to you, well, you know, kind of superfluous at this stage of the conference. It's partly a gratuitous excuse to justify the university giving me a Photoshop license. You know, why do we do catalogs? You've heard a lot of reasons, but one of the arguments I'd say is there's just so much more science. Now, okay, this is one of my best images. But, you know, Swift, in this case, is looking at this object here. This is the first relativistic tidal disruption event, for those of you interested. And there are 214 other things going on in the field of view. Now, okay, it's biased if I were to multiply this up because this is a very deep image. But even so, from this example, if you only do science with what you were looking for, you're limiting yourself to less than 1% of your potential. So it's kind of good to be able to do other stuff. But crucially, and there's a joke that I'll let you make in your own heads around U2's songs here. But, you know, if you only look at what you're looking for, you only find what you're looking for. And the problem is with finding stuff you're not looking for is you only look for the things that you know exist, if you see what I mean. How many stuff, I mean, gamma ray bursts, right? No one knew gamma ray bursts existed. And still the guy called Ray Kleberseidel said, instead of looking for Russian nukes, I wonder if there are any gamma rays coming from space. So serendipitous space is discovery space to me. It's your chance to find stuff that you didn't even know existed. And, you know, you can see examples. Peter Yonker's group found these so-called fast X-ray transients looking in the Chandra data. The QP, okay, granted the QPs were not 100% serendipitous. The first one found by Minuti was the target of the XMM observation. But since then, looking back through XMM and now EUZ data, these quasi-periodic eruptions have been found we didn't know about. So I think one of the great reasons for catalogs, and especially as a time domain person, is your possibility of discovery. So Natalie alluded to this in our discussion yesterday. I said that she'd preempted one of my slides, so I won't spend long on this, but basically catalogs are always out of date. And that's not a criticism. You know, I echo what Natalie said last time. Catalogs are really tough to build, okay? And I mean, I've got some dates up here. You know, the last Swift one, the previous Swift one I did, from the point where I said, right, stop, I'm going to define my data set as up to now, and now I'm going to start the processing. And then you start processing, and you get 2 months in, and you find a bug that only affects 1 in 25,000 fields, but it's just come up, you know, and you stop and start it again, and blah, 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 blah. 15 months to get the catalog out, and I was quite pleased with that. And now I've seen the XMM team did the last one in 6 months. I mean, I take my hat off to you. I mean, I realize you've got a bigger team than me, but even so, that's incredibly impressive. Because it's really hard. And that's not a criticism in itself, but if you're a transient astronomer, it is a bit of a bummer. Because if you take your best case scenario, right, on the 31st of December 2022, at 5 minutes to midnight, a transient goes off in the XMM field of view. And, you know, the microsecond this catalog is released, your very clever code goes mining the archive and finds this transient. I still suspect that when you put in your TOO request to the Very Large Telescope and say, hey, I've got a new transient that's 6 months old, please can you go and look at it? They're not going to be so thrilled for doing it. And that's one of the challenges. Of course, Maxi and EUZ, if Vladimir Putin would get his backside out of Ukraine, please, for lots of reasons much more important than science. But, you know, these have low latency pipelines, and we get good transient alerts out of these. But I'd like to do this for everything we can. And I just also highlight, thinking of multi-messenger astronomy, you know, you get a LIGO trigger and you look at 500 square degrees of the sky, you're going to find stuff. And you need catalogs to be able to tell you whether that stuff is new or not. And also, and I was really, you know, thank you EUZ team as well, and thank you Flick's team, upper limit calculators. You know, these aren't catalogs in one sense. These are telling you what's not there. But upper limit calculators are really vital. The importance of not being able to not just say there's nothing there, but quantify what you mean by nothing is hugely important for multi-messenger and transient work. So let me tell you a bit about Swift. Swift and I are kindred spirits in the sense that we're both hyperactive and we have the attention span of the average goldfish. Although I hear that is a myth, so maybe it should be the attention span of Phil instead. So, where XMM will spend 100 kiloseconds observing the same object, Swift averages 45 different fields on the sky per day. Now, many of those it will observe multiple times in the day because we're in low Earth orbit. So Swift basically can't keep still. Our median exposure of a given field in a day is about 900 seconds. So in terms of sensitivity, that's around 2⁻⁻13 in CGS units. And an interesting question that I actually first started asking when LIGO was about to turn on, or advanced LIGO was about to turn on in 2015, was how often do you expect, if you're going to look at 500 square degrees of sky, what are the odds of us finding a transient that's totally unrelated to LIGO? What is the sky density rate of transients? And I asked a lot of people this, and the answer I got back every time was, oh, I'm not sure. So I tried to answer it, and it turns out it's a really difficult question to answer. I reckon we might now have, and with eROSITA as well, we might now have the data to work out the answer to that. I'd hope so. It's a project that's brewing in the back of my head if I can find time. This is your archetypal trend. This is like well, not archetypal. This is the gold standard transient in many ways. One of the motivators. It's also a great example of one of the what can they say? One of the drawbacks to some of the automated, I'm all about automated approaches, right? I've made my career out of automated approaches, but they have drawbacks, which I'll show you here. Swift in 2008 was observing this object here. It was a supernova detected towards the end of 2007. And Alicia Soderberg at Harvard had requested Swift monitoring of this supernova to look at it in the UVOT. And so this was the 7th of January. 2 days later, it's observed again. And I don't know how well you can see with the light in here, but there's a new supernova gone off in there. Honestly, this is the PR, so it's like a 3-color photoshopped image. I don't think it's the best contrast image. So take my word for it, there's a new supernova gone off there. Now, the first thing is, if you are using automated pipelines, or honestly, let's be honest, how many of you, if you were analyzing this supernova, would happen to notice this other one that went off a few arc minutes away? It's easy to miss. And what Alicia did is not just that, but she had a look in the XRT data as well. These are not co-aligned with that. These are centered on the supernova. And there's this massive bright X-ray transient. And this is the shock breakout. So this is a previously only theoretically predicted point where the shock wave of the supernova penetrates the photosphere of the star and you get an X-ray flash. And there's all sorts of cool science you can do about progenitor measurements if you correlate UV and X-ray data from shock breakouts, which is why it's a great pity NASA did not select StarX a week or two ago. Just saying. You're going, what are the chances of this happening? The answer again is we don't know, but this still remains to date the only confirmed case of a supernova shock breakout. There's a few other candidates, but I'm told this is the only gold standard case. So I would suggest, given that Swift is nearly 20 years old, that the odds are pretty low, 1 in 20 years, modulo Poisson noise. But equally, if you rely on the observer to happen to check everything else in the field of view, your chances of spotting it kind of go down even more. So the idea behind this living X-ray catalog is that one should try to automate the search for serendipitous transients. I should give a quick side alert and nod here. I did my PhD on cataclysmic variables. Shout out to all the CV people in the room. Actually, I met Natalie for the first time at a CV conference in Strasbourg in 2004-ish. And there was a catalog, Ritter and Kolb. Has anyone heard of the Ritter and Kolb catalog of cataclysmic variables? They used to release it periodically, and at some point they put it on this thing called the internet, and they decided to call it the living catalog because it would just be continuously updated. And I've shamelessly stolen that living label for what I've done. But I had this idea that could we do a living catalog of XRT data? When I first proposed my plan for the very first Swift X-ray point source catalog, my boss, Julian Osborne, told me I was taking more than I could chew, and it was an overly ambitious idea. And I'm pleased to say I didn't listen to him. When I came up with this idea, he said the same again, and I kind of felt I should have listened to him because this turned out to be an absolute nightmare. But there are certain aspects of Swift that lend itself to doing something in close to real time. If you take, XMM, and this is not knocking XMM because it's entirely sensible. With XMM, you wait until you've actually finished the observation before you give people the data. I mean, that's because you're sane. You also wait until you've got all the proper housekeeping data down so that you know the data are reliable. Again, quite a good idea. With Swift, we're all about speed because, you're analyzing new gamma ray bursts and so on. We don't want to wait till the data's actually ready. So we call it quick look, which is a warning that, hey, this might be nonsense. And the idea between Swift is basically every time you downlink data, you make it available in this quick look state with this kind of warning that maybe it's not right. So this is a really, really simplified schematic. Imagine Swift is observing 4 targets a day, and I've done these in colors that I hope are colorblind friendly. I've made them as high contrast as I can. So 1, 2, 3, so 1, 2, 3, 2, 4, 1, 3, 2, 4. They're all over the place because your observing order might not be right. And periodically we downlink data. That will normally be in the middle of an observation. So when we have our first data downlink, we've got some observation of target 1 and part of the first observation of target 2 down. These go into the quick look area. They're made available for you, but they're going to change. When we get more data downlink, they're going to change. The idea behind the living catalog is that we should try to find objects with as low latency as possible. So every time we get a data downlink, we run source detection. But I daren't put it into the catalog because we alluded to this in the discussion yesterday. Source lists, when you've got dodgy positions, are a bit of a pain to do anyway. Imagine what happens if you've got a data set that's come down and your housekeeping data were incomplete, and so your data weren't cleaned properly and they're full of noise, and you put all of that noise in the catalog, and then 2 hours later you're trying to take it out again. It would be horrendous. So I have this kind of what I call a cache area, which is not currently publicly visible, but data get dumped into a cache. But we still do transient checks, which I'll tell you about now. So we don't wait for the data to be clean before we look for transients. And it's only once the data are marked as final for archive, which in theory is 3 to 7 days. It looks like it's edging towards 10. And I'm going to speak to the guys at Goddard about why that is. But when the data are marked as fully complete, that triggers it to actually go in and update the catalog. So the reality of our data flow is essentially there's a catalog which has a latency now, instead of months, or in my case years, of 7 to 10 days. And a transient pipeline where the latency is basically how long is it till the next ground station pass, plus how long it takes for the data to flow through from Goddard to us. So that's the plan. Because I added this, a number of people have put up their teams, and when Natalie gave her introductory talk yesterday and was talking about all this amazing stuff you guys and ex-members of Athena have done and show me the people involved, I was hugely envious because I'd love to do some of that lot with Swift. If any of you are bored and have some spare time and want to apply all your results to Swift, please get in touch, because basically this is the team that builds the XRT catalog. I get some support from Kim with screening fields, but otherwise I'm on my own. So let me give you a few characteristics. Of course, I can't tell you the contents of the catalog because it keeps changing. This number over here is the slowest one. That, strangely enough, the total exposure time in the catalog, because I'm quoting in megaseconds, only changes roughly once a megasecond. Otherwise, these numbers are changing all the time. So these were correct as of yesterday afternoon. So black curve, this is our sky area as a function of exposure time. So the peak is just under 5,500 square degrees. That's with at least 100 seconds of exposure time. If you wanted a megasecond of exposure time, then we're down at less than a square degree, and I'll let you read the curve off for your time of interest. The other thing about the Swift catalog is we do both the stacked and individual observations together. So the stacks are, of course, always changing, by the way. You're observing some field, and then you observe it again a week later, so you've got to redo the stack. That makes life fun. Talk to me later if you want to weep. But basically, the red histograms show the distribution of exposures per stack and the blue per observation. I should say we have one big advantage, which I'd never really appreciated properly before, but Iris was saying, and I've forgotten who spoke when he was eating now, was saying you have these point spread functions that are dependent on position. Our point spread function is pretty stable across the field of view, so I can just stack them. I've got other problems because of background, but I don't have to worry about the PSF changing between image, which is a relief. On the other hand, because of the way the background works, modeling it is slow. M31, which is, I think, one of our most observed fields now, it takes about 3 months to process. So I don't automatically update that one. I just manually do that every few lifetimes. I mean, months. Oh, yeah, I thought of throwing, because lots of people were telling you about the photons. I reckon we've got about 113 million photons in sources. I don't know how that compares to what everyone else had, but it sounded like a nice large number to me. About 300,000 unique sources. By unique, I mean not unique to this catalog, but unique in the sense that, we've got lots of times you detect the same source lots of times, so don't double count. So 312,000 unique sources, about 121,000, 122,000 of them are variable, and about 103,000 I didn't find in any catalogs, although when you've listened to what everyone's been saying this morning, there are much better ways of doing cross-correlation than I've been doing. There's a URL. There's an API to access it, and if you want to break with tradition, there's a manual online that you can read. It's in the form of Jupyter notebooks or web pages built from Jupyter notebooks that are meant to be tutorials, and they're meant to have a little bit of humor in to keep you going. So, you know, if you don't listen to me, go and read those. So how does this change? This number has a huge variation on it, okay? But the average over the last handful of years is we increase our unique sky coverage by about 0.8 square degrees a day. We get about 50 new sources a day. And like I said, 7 to 10 days to go to the catalog. This is a histogram. I probably should have made the axes bigger. 10 to the third minus 13, 10 to the minus 14. But our median flux is only about twice the size of the median flux of XMM, which is interesting because XMM's got a lot more effective area, but it's also got a higher background. So that's kind of interesting. If you take out, if I do a filter to take out all the rubbish sources and only get the gold standard sources, it goes up to more like 6, 10 to the minus 14. But still, that's not bad for a relatively small instrument. So if you go to look at the catalog, then you will see a page that looks something like this. It'll be very familiar if you've ever used the 2x SPS catalog, because I essentially copied and pasted the PHP and made a few small changes. So you get an image and some controls if you're in different bands. We don't have as many bands as XMM because we just don't have the effective area to make it viable. I believe I did try to make sure that soft, medium, and hard are kind of multiples of the XMM bands. So you could take like bands 1 and 2 added together, give our soft band or something like that. Anyone, for a prize of buying me another drink, does anyone want to know what source I'm showing you here, just out of interest? Any of you recognize the coordinates? No, no reason you should. It's FO Aquarii. This is the very first object I studied as a PhD student. My first paper was on XMM observations of FO Aquarii. So there you go. It's a nice poster child for me. Makes me feel old. So various bits of information: galactic coordinates, real coordinates, NH, all the usual stuff you might expect. If it's bright enough, we'll give you a spectral fit, or 2 of them, one with a power law, one with an APEC, neither of which are appropriate to FO Aquarii. It's a good point to make with any catalog, by the way. You know, it's impossible to give you everything you want, but if you just take, we're talking about ECFs yesterday, you know, if you just take some common spectrum for an object for which it's inappropriate, you will get inappropriate results. So, you know, brains are not optional as scientists, and I think we've probably hammered that message quite a lot. If it's not good enough to get a fitted spectrum, we can infer spectral properties from the hardness ratios and so on. We give you light curves, and this is new from 2S XPS. You can click and drag and interact with these light curves a little bit, and there's different energy bands and different binnings that you can look at them in. You can download all of these. And we give you cross matches. I'm going to pretend that we give you cross matches. I now realize from having, I've been meaning to look into stuff like N-way and arches for ages and just had no time. We do really ignorant cross matches, like nearest source wins kind of thing. But with cross matched XMM, ROSAT, SIMBAD, 2MASS, WISE, I'm going to add ERAS1 to that soon, where soon is a function of being able to find time. Other bits and bobs, of course, one size doesn't fit all. So it might be that we have not got what you want for your source. There is a link, one click takes you to our webpage to build custom products. So you can build your own customized products, or time resolved products, whatever, of the source. And you can do all of this through our Python API. I mentioned the URL already, but pip install Swift tools if you want to do more. And the UKSSDC query module lets you query the catalog and do stuff with it. However, that's a catalog. Time domain. Let's talk about transients for just a minute. Every time we get data down on the ground, immediately, whether the data are good or not, we do the analysis, the source detection, the catalog code running, and building basic products of each source, essentially to find out if there could be a transient. So we find a source and we ask 2 questions. The first one is this in a catalog? Often the best reference for Swift actually is where Swift looked yesterday, because we do a lot of repeat observations. We looked at the X-ray master catalog at HERSARC, and for our own LSXPS. I might add the ERAS1 to this, but I'm kind of hoping ERAS1 will magically appear in the HERSARC master catalog soon. If anyone knows if that is or isn't going to happen, please let me know. If it's not cataloged, you then have this question, is it new? That is, you know, when I was about 15, I, for the first time, turned a pair of binoculars to the night sky. And if you've ever done that, you'll know what an incredible thing it is. I discovered the Beehive cluster myself, just panning around the sky. I didn't discover it, though, did I? Right? Clearly, all those stars hadn't just turned on because I'd pointed my binoculars at the sky. But you have to remember that, OK, Erazita is now changing this story. But generally speaking, wow, OK, I'll move really quickly. When you point Swift at the bit of sky, it's the first time you've looked there with a telescope that's sensitive to first order. So we want to know if what we've seen is a new source or just one we couldn't see before. So this is an example of an ideal nice case. Swift detected a gamma ray burst. That's here. That was a new source, but we were looking for it. We observed it for a few hours, and then the automatic observations get killed, and we re-upload a new observation a few hours later, and this thing's turned on. And I mean, you can see by eye that it's not there before, and it looks like that cluster of pixels there. A, that's a cluster of pixels, and B, that is just off to one side, actually. You do the maths, this is clearly a brand new transient, which is kind of exciting, but it's a flare star. Now, whenever it's right on top of a red object, whenever I say things like that, someone says to me, you know what, Phil, some people are interested in flare stars. Well, good for you, and I've got good news if you are. I'm not, they're boring. Sorry. There are other transits. So I've realized what the questions we're going to have in the panel are. Sorry, I'm slightly preempting them, but I did write these slides before. There are other challenges you get. This looks like a really obvious transient, right? It's not there, then it is there. It is a transient, but actually what happened was Integral detected an object and put in a TOO for Swift to go and look at it. It happened that we'd looked at the field before. So what we found here is what Integral had already discovered. So it's not exactly a serendipitously discovered transient, is it? And also, if I go publishing an ATEL on this, the people who put the TOO in are going to get a bit angry with me. So I call this a targeted transient. That's something that we have to check out when we think we found a transient. Is it what we were looking for? You ever get other problems? So I don't have time to explain this, thankfully, but basically when you're building a catalog, you're doing a blind search. You are less sensitive when you do a blind search than you are when you just point at an object that you know exists and calculate its photometry. So what that means is when Swift discovers an object, which in this case we discovered for the first time in a blind search here, it happens that this was in a field we'd looked at loads of times before. You can now go back and essentially do what optical people will call force photometry at that position in all your historical data. And sometimes you find that the source had been detected before. So this one we've got, actually there's even a detection around there. So this is probably not a transient. If it's always been all the old detections we got are faint, we might call it an outburst. There's a bit of a philosophical argument about the difference between an outburst and a transient, which I'll save for another day. Of course, you also get other things like this. This is optical loading. So Swift does not have a filter wheel like XMM does. It only has a fixed filter. So if you observe a star brighter than about 8th magnitude, then you can get enough optical photons falling on your CCD to look like X-rays. If you want to know more, just go and Google optical loading Swift. There's a page that I've written that gives you some of the technical details. That's not very interesting. The point is that's not an X-ray transient. It's an optical source. So we don't want to claim that. There's other things, noise equivalent data, stray light, bright Earth, all sorts of things that we try to filter out, but some squeeze through. The upshot of that is that we don't issue transient alerts to you in real time. We get them vetted by a human being, for now at least, at Swift, until we can get ourselves confident in automated classification. The other one I'm going to throw out, because my PhD student Srijan is hopefully going to solve all this for us, is what I call low significance. To first order, everything you detect just above your detection threshold. That's just life. And the Eddington bias. Okay, the Eddington bias comes in. If you don't know the Eddington bias, I'm very, very happy for you. Essentially, what it means is that every source that you find near the detection threshold, you're probably overestimating its count rate or its flux. That's what the Eddington bias does. So my threshold for something to be a transient is this is a light curve bin with a normal count rate and 1 sigma error bar. If that 1 sigma error bar is above the 3 sigma historical upper limit, I flag it as a potential transient to look at. If it's less than 3 sigma above the 3 sigma upper limit, it gets flagged as probably low significance. And a lot of sources come in here. And so what Srijan's doing is some simulation work to see if we can essentially reverse engineer a better way of determining the probability that this object is actually above catalog limits and is transient. I've forgotten what I'm saying about. So last little point. Sometimes, though, it works really well. This is my poster child that I'm going to end with. This occurred just a few months after I turned it on. This actually, literally, this event was observed by Swift while I was presenting this new catalog to the XRT team, which I find quite amusing. But this is the page that we, XRT team, get to view things. So you get a few bits of information about it. And the crucial ones to me here are, it's not in the galactic plane. That tells me something interesting about it. It's 5 sigma above historical upper limits. That is, if you take the peak count rate minus the upper limit and divide it by the error, you get 5.13. It's got 32 counts, so it's probably clear of the Eddington bias. And the thing that Swift was observing was 4 arc minutes away. So this is genuinely serendipitous. And I also noticed it's got a really, really soft X-ray spectrum, looks like a black body. And actually, this is Daniela made this image for me. It's right on top of the middle of this galaxy. So everything about this screams tidal disruption event. And the reason I want to highlight this one, apart from the fact that I got a paper out of it, is this is where the story stops without the real-time catalog. Okay, without the real-time catalog, what happens is in a year's time, I release 3SXPS, and one of our postdocs called Rob, who's interested in TDEs, goes and does a search through the catalog, and he finds this thing and says, this is all the hallmarks of a tidal disruption event that we happen to miss. But because we've got a real-time catalog, within an hour of discovering this, which was about 6 hours after the observation, because the ground station passes, I had a TOO in and we were observing it again. And the full light curve of it is not a tidal disruption event. Now, our best estimate of this is that it's something called a quasi-periodic eruption, but with a period of about 25 days. I'm not married to that. It's just the least bad interpretation that we could come up with. You know, if you've got better ideas, please do publish them, because I'm intrigued by this. But the point is that by being able to search in real time, we can discover, you know, we did not know that this type of transient existed. I've never seen anything like this before. So I think I'm out of time. I'm just going to tell you, we have a low latency catalog. I want to get transient alerts out really fast, but at the moment I have to wait for a human being and go and read the manual, and I'll stop.
Fantastic, Phil. That was brilliant. Do we have any questions? Yes, I can see one at the back already. It's Axel.
Axel Schwope, mein Name. Is a transient for you only something that flashes up? I mean, you might have the other way around. A source, what was there for all the times, but is now that is now gone away. It's a transient of the other kind, and these are not least interesting.
I agree with you. And indeed, you've also got the case of a source that, you know about that periodically, you know, and as a cataclysmic variable person with my origins in that, you know, the sources that suddenly brighten up are interesting. So no, linguistically, I would argue that a transient, certainly I would think of as something that gets brighter, like drop out, it's like an anti-transient or something. If I could clone myself and not then immediately punch myself in the face, I would love to put in some extra hooks that can do things like basically look at the light curves and say, hang on a minute, where's the, you know, this is something that's disappeared or this is something that's gone into another state. I just haven't had the time to do that yet. But I think, is that something we might hear about a bit later that XMM is thinking about? Is that right? So, yeah.
Some other questions? Yeah, Angel.
Hi, I'm Angel Ruiz. You mentioned about the importance of having upper limit services. Is there something like that for Swift, or are there any plans to do?
Yep. For Swift, we have an upper limit. So if you go to LSXPS, at the top of the page, there's a link that says upper limit server. And I'm pretty certain, I'm now having second doubts, but I'm pretty certain that the live version of that actually uses the cache of LSXPS. That is up to date as it can be. You can also do it through the Python API. So if you use, you know, Richard Saxton and Ollie Koenig have built the highlight service, you can get Swift upper limits through that. Actually, if you request Swift upper limits through that, they use the API to get them from my system and sent back again. So you've got 2 routes into it.
Axel still.
Yeah.
Related question, perhaps you won't answer. There's a second instrument on Swift, UWAT. I think the latest catalog is from 2005 or so. It would be cool to have an update on this. I know you are probably the wrong person.
If you pass the microphone across the aisle to the person sat literally opposite you, Paul Cowan, Paul will take that.
So we have been processing data up to 2 years ago. I still need to validate them because there have been changes to the software. So we don't. I don't really trust that without validation to the calibration sources that the photometry is correct. But yeah, it will come eventually. We have been doing it on the side because you know, we don't really have funding. But yeah, it's coming at some point.
I think it would be fair, I look at Matt here, but you know, I said that for XRT, the team is me. For UVOT, the critical team for the catalog is even smaller, right? Because it's part of someone who doesn't even work for UVOT anymore. So, you know, it's a change. It would be great. And a question I often get asked is can we then correlate our discoveries with the UVOT? So we have, when we find a new transient, there are people from the UVOT team who do then go and look at whether there's anything in the UVOT data with us, but we don't have anything automated on that front yet.
Okay, if there's no more questions, I have a question, chairperson's prerogative, because I think we're running out of time. I just wanted to go back to this point. You talked about screening your alerts.
Yeah.
Could you just tell us how important that is, please?
Yeah, okay, that's an interesting question. Right. At the moment, I feel it's very important, but what I need to do is there's an automatic screening that happens quietly. So actually, I might even be able to, if I go back. When I had this, oh, it doesn't say, okay, it says status confirmed transient. On the page I see underneath it says auto estimate, and it tells you that. So what I need to do at some point is do a correlation between the automated assessment and the human assessment. And when the automated one, when I can get that above some level of accuracy that I haven't quite decided yet, we can get rid of it. The main fear that I have is of us accidentally publishing somebody else's transient, which is in theory easy, but if it's, say, a Fermi FGL source has got an error of half a degree, you know, it's very difficult to tell the difference between serendipitous and not, and that's where it becomes a problem.
Yeah, I agree with you. Okay.
Yeah.
We can talk about this a bit later on.
I think it'll come up.
And we're going to have to move on. Sorry. So thank you very much. Let's thank Phil again, please.